We're given the following waveform right here, and we're told that the period of this is 50 milliseconds. We need to find the RMS value of the periodic current, and we need to find the value of the resistor, given that our average power is the 24 kilowatt hour. And we are going to use this formula to find our resistance after we find our IRMS. We could plug this in. And to find our IRMS, we are going to be using this formula. So I'm just going to rewrite this as IRMS. When we're looking at our waveform, we can see that we have two parts of it. We have this part from 0 to 40 that has the same slope, so it'll have the same formula. And then we have the part that's from 40 to 50. With different slope comes a different formula. And the RMS value, IRMS, is going to be the area underneath these. And since it's the area underneath these, this is the reason why we are integrating, because we integrate when we want to find area. That's one of the times when we integrate. So we can rewrite this and plug some values in. Our first is going to be 1 over t. We know that our t is period, and it's 50 milliseconds, so we're going to be plugging in 50. And then we have our integral, and we're first integrating from 0 to 40. In solving this first part, we need an equation for this line right here. The slope of it is going to be the 40 minus 0, and since our 40 is our max, we're going to take the max of our y-axis, and this is going to be 30 minus 0. And this is being multiplied by our t. So this will be the first formula for here, and we're going to test it out because we can't know for sure here. We just have a 4 over 3 times t. If our time is 40, we will plug this in, and we see that we are going to get some big number that's not 30. But if we flip this around, instead of having a 4 over 3, and we write 3 over 4 times t, and then we plug a 40 in here, the 4 and the 40 will divide, and we'll get a 3 times 10 on top, which will give us 30. And if we plug in a 0, we're going to get a 0. So this will be the formula that we're going to use, and we just have to switch these around. That's why it's always important to test it. Now, instead of adding and doing this all over where we have a 150 like this, what I'm going to do is just write a parenthesis out front right here, and then I'll finish a parenthesis in the back. That way we just have to factor the 1 out of 50 out. And so in here, we are adding from 40 to 50. And now we need an equation for here. So we are going to set our f of x, and then we're going to do the slope again. We're going to try the same thing. I'm going to start off looking at this point. We have a 50, and on our y-axis it's a 0. So we're going to have 50, and then under this is a 0. This will be subtracted by the lowest point, which is 40, and the point tied to that on the y-axis, which is 30. And this is going to give us a negative 10 over 3 times t. Now we can try plugging some values in. If we plug in 50, we're going to get some huge number. If we plug in 40, we're also going to get some huge number, which isn't correct. So we can try flipping these again. If we get a negative 3 divided by 10. If we plug in 50 here, we're actually going to get a smaller number. We're going to divide the 10 and the 50, so we get a negative 50. And that is close to 0, however it's not quite 0. If we plug in 30, we're going to get the 10 divided by 3, and that's going to give us a negative 9. With this negative 3 over 10, if we plug in a 50, we're not going to get such a huge number. We're going to divide the 10 and the 50, so it'll give us a 5 on top. We'll have a negative 3 times 5, and that's negative 50. If we plug in a 40, we're dividing the 10 and the 40, and that'll give us a 4. So we'll have a negative 3 times 4, or 12 up top. So it's almost there, but not quite. To get it to where it should be, what I'm going to do is add to this. And it is really easy to forget what we're plugging in, but if we want to get 30, we're going to plug in 40. So just keep using 40 as the test value here. And if we multiply 3 and 40 before dividing anything, we're going to get 120. Well, if we don't divide by 10 and we just have a 150 here, that will give us 30. And we can try the same thing where instead of having a 40 here, we have a 50. So if we have a negative 3 times 50, we're going to get 150. And negative 150 plus 50 is equal to 0 right here. So that will be our equation. We're just going to get rid of the 10 right here, and we're just going to be left with a negative 3 times t plus 150 as our equation. And we can plug this into here. and that will be our entire equation. Also, the reason why I'm not worrying about units converting it from milliseconds into seconds for it to be amps or anything is because if we have, like, let's say this is 50 milliseconds down here, which it is, the period is 50 milliseconds, and then we have the time in here, which has the unit of milliseconds, and this is in the numerator. Well, if we factor this out of our numerator, because it's a constant, it will cancel out with this milliseconds. So the milliseconds will cancel out, and we're just going to be left with seconds. So continuing forward, I'm going to look at this first expression, and then I'm going to factor out the constants. And for this one, to make it a little bit simpler, I'm going to do a U substitution. For the U substitution, I'm making all of this equal to U. So I'm going to say that we have a U is equal to negative 3t plus 150, and then I am going to derive this. So we're going to get du is equal to negative 3 dt. Now we want to get dt, so we're going to have our du divided by negative 3 is equal to dt. And then we can plug this in here, and we're going to have a negative du over 3. So when we solve for this part, I'm going to factor out the negative 1 over 3, that is with the du, and then integrate our u. And then we're going to get u cubed divided by 3. And remember, this is going from 40 to 50. And I forgot the first part, but it's going from 0 to 40. And this is going to be our new equation. Now before we solve for this, I'm going to combine some of the constants together. That way it's easy when we do our final equation. And remember, before we do any of this, we substituted this for our u. So when we are writing our equation out, we're going to have to plug this back in for u. Or if we wanted to, we could just write these boundaries in terms of u. But for this problem specifically, I'm just going to plug back in our equation. And this will be our final equation that we can plug into our calculator. And if we do this very carefully, we are going to get that our answer is equivalent to approximately 17.3, and this is amps in RMS. And we can use that information to solve for this formula right here. If we plug this into our calculator, we know our P average is 24 kilowatts. So this is going to be 24 kilo, which is 10 cubed. And we want to find the resistance, so we are going to divide this by the current. And we know our current to be 17.3, and this will be equal to our R. And make sure you square the bottom as well. That's very important because our IRMS is squared here in the formula. And if we do this, we are going to get approximately 80. And if we do this, we're going to get approximately 80 ohms of resistance. So the upper part is the first part of our problem, and the part on the right side of our corner is the second part of the problem. And that's how you would go about solving for this problem.